Section 2.3, linear equations. By definition, a first-order differential equation will be of the form a1 divided by dx plus a0 y equals g of x, where a1 and a0 are coefficient. Y is the dependent variable and x is the independent variable. The standard form of the first-order differential equation will be dy by dx plus the coefficient px times y equals the function f of x on the right-hand side. To solve the first-order differential equation, make sure we write it in the standard form, where dy by dx plus p times y equals f of x. Identify the function p and the function f. Find the integrating factor mu as e to the integral px dx. Use mu in the formula to find the general solution y, which is in the form of y equals 1 over mu times the integral mu times f dx plus c as a constant of integration. Any term of a solution approaching to zero as x approaches infinity is called a transient term. To identify the transient term, we take the limit of the terms in the general solution as x approaches infinity. If it is approaching zero, therefore, that term is called a transient term. It could be all terms or some terms within the general solution as a transient term. The homogeneous first-order differential equation, where the gx on the right-hand side is zero. If gx on the right-hand side is non-zero, we call a non-homogeneous first-order differential equation. Let's look at the first example. We are going to find the general solution of the given differential equation, and then determine whether there are any transient terms in the general solution. This equation is already in the standard form. The dy by dx plus px times y equals f of x. Right on the side, our px is -2, and the f of x is x squared plus 5. Next, we find the integrating factor. The integrating factor mu is e to the integral px dx, or e to the integral -2 dx. We get mu equals e to the -2x. And next, substitute mu in the formula to find the general solution of the differential equation. Y equals 1 over mu times the integral mu times f of x with respect to x plus c. C is the constant of integration. Replace mu with e to the -2x, and the f of x is x squared plus 5 with respect to x plus c. In this case, we are going to use the bypass technique. Use Liège to identify the u and dv. Exponential e to the -2x is the exponential function. The x squared plus 5 is the algebraic function. In this case, the algebraic is in the polynomial form. We are going to use the tabular bypass to help us find the antiderivative. As u x squared plus 5 on the left column, e to the -2x as the dv on the right column. The left column, we are going to find the derivative until we get 0. The right-hand side, we're going to find antiderivative until the last row. So the left-hand side, x squared plus 5 By the derivative, we get 2x. Keep going, we get the next derivative as 2 and the last derivative 0. That's the end of the table. And then complete the right column. E to the negative 2x, the antiderivative, e to the negative 2x over negative 2. Keep going. E to the negative 2x over negative 2 is antiderivative. We'll have the denominator 4 instead. And then the last antiderivative, we have e to the negative 2x divided by negative 8. By tabular by parts, the first left multiplied by the second right column with the plus sign for that product in front of that product, and negative and positive alternatively. So the general solution y is e to the 2x as we write the negative power as a reciprocal of the positive power. And the integrand e to the negative 2x x squared plus 5 give us the first product as x squared plus 5 multiplied by e to the negative 2x divided by negative 2 minus 2x times e to the negative 2x over 4. And the last product would be 2 times e to the negative 2x divided by negative 8 and plus c. Multiply e to the 2x to all terms. Quantity x squared plus 5 multiplied by 1 over negative 2 or divided by negative 2. The second term, 2 and 4 reduce. We have negative x over 2, e to the negative 2x and e to the 2x cancel, minus 2 over negative 8 becomes negative 1 over 4. And the last term is c times e to the 2x. And we obtain the general solution. For part A. And next part B, we are going to determine the transient term. And we're going to look at each term by taking the limit. So the limit of x squared plus 5 over negative 2 as x approaches infinity. This one will return infinity, so it's not the transient term. Next, the limit negative x over 2 as x approaches infinity would return the value approaching infinity as well. The limit of negative 1 over 4 as x approaches infinity will be negative 1 over 4, so not equal to 0. Let's put it this way. And then the last one, the limit of c e to the 2x as x approaches infinity will approach infinity, which is not equal to 0. Recall c is the constant. Therefore, there is no transient term for this general solution. The other way we say the solution will not reach an equilibrium point or will not reach the result 0 eventually.